In the present lecture, we will discuss the equivalent modulus of a composite bar. So let's see in the diagram. Figure shows a compound bar of length capital L consisting of two materials of modulus value of E1 and E2 and having the cross-sectional area of A1 and A2. Similarly, another diagram is represented for the equivalent bar. The equivalent bar of length L and made up of a material having the modulus value is capital E and its cross-sectional area capital A equal to the A1 plus A2 as shown in the diagram. So next we have to determine the deformation of the equivalent bar. We know deformation delta equal to the PL by AE. So first we have to see the for equivalent bar, P is the applied load and L is the equivalent bar length and cross sectional area of the equivalent bar is the A equal to A1 plus A2 and E is the Young's modulus of the equivalent bar. Then deformation delta equal to PL divided by A1 plus A2 into E. So this can be written as PL by delta equal to the A1 plus A2 into capital E. So let's consider this is the equation 1. We determine the PL by delta value for the equivalent bar, that is PL by delta equal to A1 plus A2 into E, and this is the equation 1. Similarly, we determine the PL by delta value for the compound bar, and we know that while solving the compound bar problems we are using the two conditions. One is the equation of compactability, another one is the condition of equilibrium. So equation of compactability is, so delta 1 equal to the delta 2. So that is deformation of the first material is equal to the deformation in the second material. Then delta 1 we can be written as PL by A1 E1. Delta 2 we can be written as PL by A2 E2. So L will be cancelled and P by A1 is the sigma 1 and P by A2 is the sigma 2. So this relation we can be written as sigma 1 by E1 equal to sigma 2 by E2 and sigma 1 becomes the sigma 2 into E1 by E2. So next we have to use the condition of equilibrium. So condition of equilibrium is the, so load applied on the compound bar equal to the load on the first material and load plus load on the second material, that is, and we know load equal to the stresses into cross sectional area. So condition of equilibrium says that sigma 1 A1 plus sigma 2 A2 equal to the P. So we know sigma 1 equal to sigma 2 into E1 by E2. Then substitute sigma 1 value in the condition of equilibrium. Then condition of equilibrium equation will becomes the sigma 2 into E1 by E2 into A1 plus sigma 2 A2 equal to the P. Here sigma 2 take the common, then sigma 2 into E1 by A2 into A1 plus A2 equal to the capital P. Then sigma 2 equal to P divided by E1 by E2 into A1 plus A2. And we know in the compound bar delta 1 equal to the delta 2. Let's consider that is the delta. And this is we can be expressed in the terms of the sigma 2 value. So that is the delta equal to sigma 2 L divided by E2. So next delta will become the, we substitute the sigma 2 equation. So this is the sigma 2 value. The sigma 2 value you have to substitute in the delta equation, then delta will become the P into L divided by E1 by E2 into A1 plus A2 into the E2. then delta will become the PL by A1 E1 plus A2 E2. And from the here PL by delta value becomes the A1 E1 plus A2 E2. So we determine the PL by delta value for the compound bar as well as we determine the PL by delta value for the equivalent bar. So now we have to equate this PL by delta value. So PL by delta value from the compound bar, it is the A1 E1 plus A2 E2. Similarly, PL by delta value from the equivalent bar, that is the A1 plus A2 into the capital E. Then we have to equate these two values, that is A1 E1 plus A2 E2 equal to the A1 plus A2 into the E. So from this equation we can be written as, so Young's modulus of the equivalent bar capital E equal to the A1 E1 plus A2 E2 divided by A1 plus A2. So this is the very important equation. In general many competitive exams it will be asked, and most of the times we will be use this equation for solving of the composite sections bar. Okay, so let's see the one example problem. Let's see the problem. A compound bar is made by fastening one flat bar of steel between two similar bars of aluminum alloy. So this is the schematic representation of the compound bar, which is consisting of flat steel bar and fastening in between the two similar bars of aluminum alloy. The dimensions of each bar are 40 mm wide and 8 mm thickness, so that cross section of the composite bar measures 40 mm into 24 mm. So here it is given the cross sectional area of the composite bar, that is 40 mm into 24 mm, and also given the cross sectional area of the aluminum and steel bar. And next it is given the E value for the steel is 2.04 into 10 to the power 5 Newton per mm square, and E value for the aluminum is 0.612 into 10 to the power 5 Newton per mm square. So let consider suffix S for the steel, that is ES equal to 2.04 into 10 to the power 5 Newton per mm square, and suffix A for the aluminum, that is the EA equal to 0.61 to 10 to the power 5 Newton per mm square. Find the apparent value of E value for the composite bar loaded in tension if the respective elastic limits for the steel is 230 Newton per mm square and for aluminum is 50 Newton per mm square. Find the elastic limit of the compound bar. So here we have to determine the Young's modulus value for the composite bar. Moreover, we have to determine the elastic limit of the compound bar. So first we have to determine the E value for the composite bar. So in the previous derivation we seen the E value for the composite bar is the A1 E1 plus A2 E2 divided by A1 plus A2. So here first material is the aluminum and second material is the steel. So this is the E equal to AA, so A suffix A, and EA plus ASES divided by AA plus AS. So we know the cross sectional area of the aluminum and steel. For aluminum, so it is the two bars and each one having the 8 into 40. So total cross sectional area of the aluminum bar is the 2 into 8 into 40, that is the 640 mm square, and the steel bar is having the only one only, so its cross sectional area become the 8 into 40, that is the 320 mm square. And also in the data it is given the Young's modulus of the aluminum as well as the steel, EA value and ES value. Then substitute these values in the equation of E. So we will get the Young's modulus value of the composite section is the 1.088 Newton per mm square. So next we have to calculate the elastic limit of the compound bar. So elastic limit of the compound bar is the stress at which one of the members, either steel or aluminum alloy, is stressed to its elastic limit. So elastic limit of the compound bar is among the two materials, steel or maybe aluminum, among these two, which one we will get the minimum value, which is having the stressing, that is we have to consider the elastic limit of the compound bar. So let's see the solution. And in general, while solving the compound bar, we are using the two conditions, that is the condition of compactability and equilibrium condition. So that is the deformation in the steel equal to the deformation of the aluminum alloys, that is the delta S equal to the delta A. So previous we seen delta S we can be written as sigma S L by ES. So L is the common for the both of the materials, so that's why it's cancelled. So then sigma S by ES equal to sigma A by EA. So then sigma S is sigma A into ES by EA. We know ES value and the EA value, then substitute, then we will get the relationship between the sigma S and sigma A, that is sigma S equal to the sigma A into 3.333. Okay, next we have to see the another condition. So equilibrium condition, that is the total applied load on the composite section equal to the load on the steel plus load on the aluminum. So load we can be expressed, so stress into area, so sigma S AS plus sigma A AA equal to the total applied load P. So we know the sigma S and sigma A relation, that is sigma S equal to the sigma A into 3.33. Substitute here, and also we know cross sectional area of the steel as well as the aluminum. Then this equilibrium condition equation we can be written as sigma A into 3.33 into 320 plus sigma A into 640 equal to the P. So then we can be express sigma A value in the terms of the P. So sigma A equal to P divided by 1706.6. So we know the relationship between the sigma A and sigma S. Similarly, sigma S also we represent in the terms of P values. So sigma S equal to P divided by 512. We determine the sigma A and sigma S values in the terms of the P. So next let's consider sigma equal to the elastic limit of the compound bar, and we can be express elastic limit of the compound bar in the terms of the P, that is the relation is the elastic limit of the compound bar into total cross sectional area of the compound bar, that is the cross section area of the steel plus cross section area of the aluminum equal to the total load applied on the compound bar, that is the P. So then sigma into AS plus AA equal to the P. So we know AS value is the 320 and AA value is the 640, total is the 960. So then the relation between the sigma and the P is the sigma 960 equal to the P. And we determine the sigma A and P relation, that is sigma A equal to P divided by 1706.6. From these two equations we can be equate the P value, then we have to equate the sigma 960 equal to the 1706.6 into sigma A. So from this equation I have to say that sigma equal to 1706.6 divided by 960 into sigma A. Sigma A is the elastic limit of the aluminum, that is given in data, that is 50. So sigma value is the 1.778 into the 50 and value is the 88.89 Newton per mm square. Similarly, we have the relation sigma and P, that is sigma into 960 equal to P, and also have the relation sigma S equal to P by 512. From these two equations we have to say that sigma into 960 equal to 512 sigma S, and sigma will become the 0.533 into sigma S. Sigma S is given in the data, elastic limit of the steel, that is the 230 Newton per mm square. Then sigma will become the 0.533 into 230 equal to the 122.67 Newton per mm square. So here we got the elastic limit of the compound bar. Two values we got, that is the 88.89 Newton per mm square, another one is the 122.67 Newton per mm square. Now elastic limit of the composite bar is the, among these two values, minimum value you have to say that elastic limit of the compound bar. So elastic limit of the compound bar is the 88.89 Newton per mm square. So this is the solution, and thank you.